So let's get started, everyone. So welcome back. So we're starting a new section of the class. So this one's going to be on clustering. So this is a kind of a different way of doing data analysis than we've looked at before. So we've kind of looked at a bunch of these kind of fundamentals, and then we looked at regression and dimensionality reduction, and then we're going to look at two more in this semester. One is clustering, and then one is the last one will be classification. So this will be kind of the intro lecture into clustering, and to kind of ground this discussion, we're going to kind of have a kind of part of this lecture will be a sidetrack into this concept called that's going to be called a Voronoi diagram. I think this is really essential to understanding these assignment-based clusterings that we're going to be talking about. The same way we spend a lot of time thinking about what is a projection when we're in high dimensions dealing with dimensionality reduction. The Voronoi diagram represents the same sort of kind of operation that's going on as a projection, but it's got some more kind of nuance to it. So we'll kind of look into this in this lecture today. We'll also define kind of the general kind of what is clustering and all of that sort of stuff. Okay, so before we start, let's look at the schedule of the class again, as we often do. So first of all, homework 4 is going to be due in about a week. Okay, so hopefully a lot of you have started on homework 4 already. If not, I'd suggest starting on that soon. This is again one like homework 3, which will take a little bit of time to do. You'll have to kind of work a little bit with the Python to implement kind of doing regression through gradient descent, which is really, will be a really kind of great preparation for doing the stuff in the machine learning class. Hopefully many of you will get there, and you do a much more advanced versions of this. So kind of make sure you start early on this. Again, if you are having kind of been fighting a little bit with the Python and that's been kind of getting in the way, so TA Hassan has put together this nice tutorial on Python. It's linked off of the main page here, also posted on Canvas. So please go through that. That'll allow hopefully the snags you may have been dealing with and getting started with that. There'll be a lot of ways to kind of get through that. So those things become a bit easier. Okay, so the other thing is quiz number 5 is going to be next week on Monday, kind of at the end of class again. Again, we'll open at 2:30 and be until 11:59 at night. You'll have half an hour to take it. You'll get one side of a sheet of paper, and then you are. So this quiz is going to be just on the dimensionality reduction part of the course. Okay, we extended this period where we're going to be what's being covered here. We had the extra break around election day. So this lecture is not going to be covered on the quiz. It'll be factored into the next quiz, which will be the last one. Okay, so quiz number 5 is going to be in class on Monday. So don't be surprised when there's a quiz on some Monday. And please remember to take it on time. Yes, okay. So that's where we are in the class. We're getting towards the end. We've got about a quarter of the semester left. And I think some of the most exciting material is yet to be covered. But now we have a lot of the background needed to really kind of dive into it and understand it properly. So, okay, so we're going to be talking about clustering. Okay, so let me start by saying I've not really defined what is clustering. So what is clustering? Okay, and I will ask this question on the slide. I'm not going to be able to entirely answer it. Turns out the answer to what is clustering is not nearly as clear as the answer to what is regression or dimensional reduction or classification. Clustering is this kind of behemoth of an area. There's a lot of kind of ill-defined notions and things people do that fall under the category of clustering. I would say much more so than a lot of these other areas. Classification is similarly broad in the type of techniques people use, but the kind of the input and output objective in that sense is going to be often much more clear than the case of clustering. You know, in our department, we essentially offer 2 advanced courses in these areas. Basically, the machine learning class is basically mainly about classification, and there are some follow-on classes to that. We also offer another grad level class just on clustering. It's a really broad area. So what is clustering? Okay, think of the input. Now the input is going to be a set of objects. We'll call this X, X1, X2 up to Xn. Okay, we're going to have a set of these objects, and we'll probably also, typically, we're going to have a part of the input is typically going to be a distance that's going to be defined a function d that goes from x cross x. It's usually defined between two of these elements, right? And it's going to give us some real value, which is positive. Okay, so it's going to some distance that says how close are 2 objects. Okay, it might be defined in the domain the objects come from, so slightly more general. And in this class, we're going to look at objects which are vectors in RD. Okay, but in general, that's not the case. In general, people look at other objects. They can look at, okay, how similar are 2 trains? I don't know. Those aren't vectors, but you might convert them to vectors in some way, and then look at the distance, and but here we're going to be given the input as this distance, and in this class, this class only, we are going to say that X is going to be a subset of R. See, I've used here. How would I call this distance uppercase D, and then we can say this is RD, and we're going to say that this distance between 2 elements, x1, x2, is going to then be the Euclidean distance, x1 minus x2. Okay, so we're going to make this assumption in this class. This will allow us to focus on still a fairly big subset of the types of clustering, but this is in general not always the case. This also, I'll highlight, this gets rid of this problem of, well, right, this distance is defined as the Euclidean distance on the vectors is the right way to measure the similarity between these. This is going to be another unsupervised problem. Getting closer to what the output is supposed to be. Another unsupervised problem, so we're just going to be measuring how well do we capture the structure of the data. And with dimensional reduction, I really stress this point that this, if the coordinates didn't mean the same thing, they different units, then this was kind of a very ill-defined operation here. And the same thing is going to happen in this case, except we're going to assume in this class, again, we're going to assume that the input, that the data is given to us in some way where we can use the Euclidean distance to measure this similarity between objects. If that is not the case, we're again going to get into trouble, right? If ill-defined, then we're going to get into some trouble. Okay, we're going to be comparing the number of apples, the number of oranges, right, and saying that those are comparable quantities when they might actually not be. Okay, so, but we're just going to assume that this is the case. In a number of clustering formulations, you can plug in something other than Euclidean distance, a scaled Euclidean distance, or kind of an L infinity distance or L1 distance, and these things are going to work, but not always. The main thing we're going to talk about in this class is going to be, in this particular semester, is going to be called Kmeans clustering, and that's going to actually need this to be so Euclidean distance. Otherwise, things are going to fall apart, and we'll explain exactly why that is the case. So it's going to need that this is going to be the Euclidean distance in this class for the K-means clustering. The main kind of algorithm for it to actually work assumes that these are Euclidean vectors and Euclidean distance. There are some other cases which can work, but this is kind of, everything is simpler if you just think about this as Euclidean distance. Okay. So this should be familiar input now, right? We have vectors and RD, and we can take the Euclidean distance between them. Now our goal, okay? This is going to be a little bit vague, and then we'll specify it to be more concrete here, is going to be K kind of subsets. And we're going to call these, I'm going to make sure I get the notation right to follow the book. We're going to call these subsets x1, x2, up to xk. Okay, each subset xi is going to be a subset of x. Okay, we're going to find these k subsets. In this case, we'll be given the parameter k. So I'm going to say that this is often, so usually part of the input. So we're usually given the parameter k. We'll discuss if you aren't given this parameter k kind of in a probably next lecture. So okay, so we're going to find these k subsets, okay, and then we're going to say we want that the for xi prime in xi, we want the distance xi prime to be small, and for xi xj, let's say for xi in xi, xj in xj, right? So for I not equal to j, then we want the distance, should be uppercase D, maybe consistent, the distance xi xj to be so large. Okay, so in general, we want that if 2 points are in the same cluster, right? If they're in the same cluster, we want them to be, their distance to be small, and if they're in different clusters, we want the distance to be large. Okay, so we want to kind of find a grouping of points, okay, where points that are close to each other are in the same cluster, points that are far from each other are going to be in some different clusters. Okay, so this is generally the goal. I'll specify this further and get it back to something that looks like sum of squared errors that we're all used to. But there are lots of type of clustering, and we will mainly focus on these ones based on sum of squared errors. Although I will show at least one variant that does something very different, just to give you a flavor of that. And if you take the data mining class or the clustering, graduate level clustering class, then you will see a whole bunch of other variants that do a whole bunch of other things, okay, that generally follow this goal. Okay, so let me try and draw a picture. So it's quite common to start with some picture that looks like this, where this is, say, x1, x2, x3, x4, x5. These are all of my data. This is my input data set X. Okay, and then for clustering, the goal of the clustering, these are the data elements. What I would like to do in general is to identify this as maybe cluster X1, this is cluster X2, and this is cluster X3. So we'd say X1, these are uppercase, X2 and X3. These are the clusters for K equals to 3. Okay, so this is the typical picture that you are usually shown when you're thinking about clustering. I will show something in Python, hopefully towards at the end of the lecture, where you can see, again, a picture in Python that looks pretty much like this, but we generate with Python, and okay, this picture is very common, and it kind of gives you some base intuition. We want the property that, say, these distances are small, right? And let's see, these distances in between 2 points in the cluster, this would be xi, this is xj. This, I want this to be large, right? These are points across 2 clusters, right? The green one is points within one cluster. Those should be small, right? So in general, this is right, but there's a lot of reasons why this picture, I think, is kind of deceiving when you get past very simple examples. For simple examples, this is fine. That's what it is. It's a simple example. But with clustering, you often deal with more abstract objects with more abstract sort of distances between them. You might be in higher dimensions, and data might not be shaped this way, right? A lot of the data we looked at earlier in the class, it was fitting through a line with linear regression, or there was a subspace we found with dimensionality reduction. It didn't look like this, where there were these 3 groups of points. So there are not always going to be clusters, right? A lot of people say, I'm going to run a clustering algorithm, I'm going to find my clusters, and sometimes there just aren't clusters in the data set. So regression, you can always fit a best model, and you can kind of measure how accurate you're doing with the generalization using our cross-validation techniques. So dimensional reduction, when you're in high dimensions, just kind of based on certain statistical properties about high dimensional data, there's almost always low dimensional subspaces that capture most of the variation. It's actually pretty hard to, unless you're constructing it very carefully, to construct things that don't have kind of low dimensional structure. But with clustering, it's quite common for the pictures not to look like this. And what's more so, you're often in higher dimensions where you can't draw this picture, right? I can go back and I can do PCA and I can get a 2-dimensional picture, and I can hope it looks like this, but it could be that there's another cluster that doesn't fit in the best 2 dimensions I can draw. And so when I project it down, it covers these overlaps with these other clusters. So maybe there is clusters, but you can't see them, or maybe there aren't clusters. A lot of times there's just kind of one blob of points, or they're along a line or a subspace. And so a lot of times people try to kind of force clustering onto a problem when it doesn't really fit. Okay, so this is part of my kind of warning about clustering. Okay, so, and again, I haven't really told you how to quantify how well you're doing. I'm gonna kind of build up to that as well. Okay, so I want to kind of, again, talk about this in the context of the other methodologies we've seen so far. We've talked about, so regression, okay? And so in this, remember the input was x, y, and we built built some function from this x and x And so this would give us this y hat, right? And so then we could measure, this residual on a data point, we could measure this as yi minus yi hat, right? We could measure it just in this y value that we actually predicted here. Okay, so we had a nice way of measuring how much error we had. And maybe it was y hat minus y, but that didn't matter. We have, basically we have this space, we have x down here, which could be kind of RD, could be multidimensional, maybe before or after I've done a polynomial expansion, and I've got this y coordinate, and I'm fitting some model through here. This is this function from x to y, and I've got some data points, and I can measure this residual, right? This was this Ri. It kind of made sense as measuring in this vertical direction. That was pretty clear. Okay. So dimensionality, so reduction, okay, and in particular with PCA, okay, then what we had in that case, well, we had x in, which is going to be a subset of RD, and I guess I called this, was a subset of RD, okay, and we wanted to find B, which was again in RD, but was rank equals to K, so a K-dimensional subspace. So I think of having this high-dimensional data, and then I found this model subspace here B, which I could represent this by these vectors V1 and V2, and I could take all of my data, and it made sense to project it down or up onto the space. And again, these projection here, these are not necessarily the y direction projections anyway, but this again would measure this residual, and I was trying to minimize, say, the sum of these squared things, right? So again, in this case, the goal was in regression, I wanted to minimize the sum of the squared of these residuals, and again here I will want to minimize the sum of these squared, so of these residuals. In this case, this was equivalent to a minus ak, the squared Frobenius norm. Okay, so if I found the best rank K subspace, A sub K, or that was the projection, maybe this was equal to, there are a variety of ways of trying to express this, but this was, I could also say the projection onto the subspace defined by B and minimize the squared Frobenius norm. That's again the sum of these squared residuals. Okay, so I want to come up for clustering, and in this class we're going to focus on a similar formulation where it's going to look like the sum of these squared residuals here, but we're going to do this over these sets instead. Okay. Okay, so how are we going to do this with clustering? We're going to do this with a family of clustering called assignment-based, clustering. Okay, and there are a family of things here. Okay, and now we're going to have an input. X is going to be in RD, and we're going to have some, distance, which is going to be defined as the Euclidean distance. So that's minus, maybe that's not clear what I'm writing there. Xi, xj is equal to xi minus xj, right? So we're using the Euclidean distance as the distance. Okay, and now we're going to have a set of these points on. So we're going to have this, and then k clusters. So we'll say k is going to be a number of clusters. And we're going to have our input as this set of points. Okay, and if it looks good like this, then this is how we want the data to look if we're running clustering. Again, there's assuming that there are clusters if you're running this. Okay, and now our model that looks like before, this was a function f, which is often thought of as a line in two-dimensional space, but is really a function, or a subspace B, right, in the dimensional reduction. In this case, the model M is going to be a set of points, okay? And we're going to call these, so these sites, okay? I'll say the model is going to be S, which is going to be these K sites, S2 up to SK, and these are going to be a subset also of RD. Okay, this will be S1, S2, S3. I'm seeing this now. The blue and the black don't have a lot of contrast, but I drew the sites to be a little bit, so they're a little bit larger here. Okay, so this is going to be the model. And now our residual for all the points is going to be the distance to this point at the center. Okay, for all the points, this is going to be the residual. Okay, so the residual in general, the residual will be the Euclidean distance between xi and some site sj. Okay, now the question is, before, in the case of dimensional reduction, right, this, we could write this as the sum over I equals 1 up to n times ai minus projection onto b ai squared, right? So we could write it as this sum of the projection. We need to do something like a projection operator here to determine which site to map it to. Okay, I can't just, I have to pick one of the sites to go onto. I don't have a nice kind of subspace where I can define this projection operator anymore. So what we're going to replace this by is xi minus, I'll call this a phi of the set S of xi. Okay, so this is going to be the residual. And this operator, this phi of S, is what we're going to basically talk about for the rest of the lecture, or most of the rest of it. This is, so phi of S x, need more space here to write this out, I think. Okay, so phi of S x is equal to the, I'll write this here and then I'll spend more time explaining it. S I in S, which minimizes x minus Si. Okay, so it's the closest of the sites. Okay, it's going to be the closest site, right? So and that really captures what's going on here. I'm going to get these 3 clusters worth of points, and this works because every point maps to its closest site. That makes sense. And it's very similar to the case of the dimensional reduction, where I map to the closest point onto the subspace. right, as the closest point onto the subspace, but we knew that was this projection operator, that because it was an orthogonal projection, then I could define this with dot products and these basis functions in this nice way, and it gave us this extra structure. That was nice about the dimensionality reduction. Now I'm doing this with so let's say it maps to the closest site. So actually, I did this wrong. This should be an argmin. Okay. So I'll expand this on the next slide here. Okay, but that's what's going on. I'm finding the closest site, and then I'm measuring the distance to the closest site. That's my residual, and then we're going to do something like minimizing this sum of the squared errors again. But I'll come back to that and talk about that slightly more broadly. Okay, so let's come back to that at the end of the lecture. So let's talk about this. Let's call this the post office problem. Okay, we're going to find this phi function, phi of s of x, which is going to be the arg min of little s. We'll call this si, or let me say call this guy sj, of the distance between x and sj. Okay, so I want to find for a point x, this is the function which goes from a point in RD in this case to one of the sites, right? So phi of s is going to be a function which goes from RD, that's this set of potential input points, into the set S. So it's giving me one of the sites. Right, the output is one of the sites, and it's going to be the closest one, the one that minimizes this distance. And we'll see that actually this isn't always well defined. Sometimes there's more than one which can satisfy it. It's going to turn out I'm only going to need the distance most cases, and that will be actually this will play into the algorithmically. So for measuring the residual, I only need the distance. But in the algorithm, I'll actually need to know which of the sites. So I actually need the argmin. So I typically write it this way, so I'll use this to return the closest of the possible sites. So in the data mining course, you'll look a lot more at versions of this function phi of s. This is called the like the nearest neighbor problem, where I want to find the nearest neighbor from some set. And kind of the first 5 or so lectures is talking about variations on this problem, where you find nearest neighbor for things other than Euclidean distance, and you can kind of plug this formulation in here in general. But Euclidean distance is kind of the most commonly studied thing, sort of problem here. Okay. Now, the post office problem is to try and define this function, okay? Let's look at the case where d is equal to 1 here, okay? So I'm going to have, this is going to be R1, and I'm going to have sites S1, S3, S2, and S4, okay? And now I'm going to be given a data point, X, okay? And I want to find the closest of these, of these sites, okay? And this function phi of S is going to map it onto site 2 because that one is the closest, okay? I think it's good to start thinking about it this way, because in 1 dimensions, if you've taken an algorithms class, you might think, okay, I could actually solve this fairly quickly, right? If the number of sites becomes big, within the algorithms, we're going to need to solve this problem, efficiently, actually. If the number of sites becomes big, I can actually solve this solvable in, so O of log k time for the size of S equals to k. Okay, I could solve this in log k time. I could build a binary tree on top of here, and I can kind of do walk down the binary tree until I find the closest left and the right neighbors. I know it's in between S2 or S4 if it falls here based on some following down a binary tree, and then I can check the distance to both of those. And this takes log k time to compute this nearest neighbor, right? So doing this would be great. It would allow us to kind of do this operation quickly, and the structure of it seems pretty reasonable. In general, what we're going to want to think of is to define what is this structure here, okay? And the post office problem kind of gives you this structure. It's this non-uniform decomposition here. So if I want to, let's see, pick out S1, then its region of the plane for all values x which fall in here are going to be mapping into S1. Okay? If I pick out, let's say, S2, right, like x fell into S2, then it's going to be this whole region, all the values of x which fall in here are going to map onto S2, right? And so there's this decomposition of the line into these regions, and everyone goes to their own, so their closest post office, right? So the idea is you want to have a bunch of post offices and divide up the space so you know who is assigned to which post office, which is your closest one. That's not actually how they assign you a post office. There's a thing called zip codes which do that, and they try and put the post office in the middle, but it's not perfect. But this is what the post office problem is. We need to find this decomposition, and you'll see that it's not completely uniform here. If I look at, say, this thing around S2, it goes further to the right than it goes to the left because S3 is nearby, right? So I need to find kind of the bisector in between these, right? And this is what is dividing this up. Okay, so I want to think about this, but I want to take us to a little bit higher dimensions, because this is really defining this phi of s is like this projection operator, but now we need to use this for assigning our clusters. So what does this look like? How are our clusters assigned? In 1D, I can kind of understand all the data points assigned to each one of these cluster centers of the sites here. But let's see what happens if we're in a slightly higher dimension here. Now we're going to say d is equal to 2. Okay, and we're going to kind of have a bunch of these sites. And let me see if I can make this so it's kind of interesting. Okay, so now I'm going to have sites S1, S2, S3, S4, and S5. Let's put another one up here, S6. Okay. That one looks a little bit, that's going to be a little bit odd. Let's put it right here. Okay, so now I need to kind of solve this post office problem for points in two-dimensional space. And this is going to look slightly differently. I can draw like the bisectors between a couple of these things, but it's not just dividing it into this line anymore. Okay, the bisector here looks this way, but at some point I'm going to have all these different bisectors. Okay, and some of these are going to extend, and then they're going to meet. And now this is actually the bisector between down here between S3 and S5. Okay, and S3 and S1 has this bisector. and these should look kind of like this. Let's just kind of meet at a vertex here. Okay, and there's some much more interesting structure that's going on here. Okay, so I'm going to divide the space up here now. Okay, and now I want to say for, let's say, for S5, I want to look at all the points which are assigned to S5, and it's going to be in this region here. There we go. All right, let's fill in this region. Good. So this is called the Voronoi Voronoi cell of S5, right? So this pink region is all the points which are closer to S5 than to any other point. Okay, and so when we're going to define our clusters based on this, assign them to the closest point, they're kind of carving out these regions of space, right? And this entire kind of decomposition is called the Voronoi. So it's called the Voronoi diagram. Okay, and so this is basically equivalent to this phi of S function, which is at the core of these clustering things, the same way this projection function was within dimensionality reduction and doing PCA. Okay. Okay, so if we want to understand clustering, it seems like we kind of need to understand this function to completely understand what's going on. And so if you go and you try and completely analyze these algorithms and get into the nitty-gritty of why they're working and when they're working, it actually comes down to like looking at this like Voronoi diagram of these sort of sites. Okay, so I'm going to spend the next 5 or 10 minutes telling you about it, and then we're going to kind of learn that it's in this case in 2D it's going to be kind of nice, and in higher dimensions it's going to be less nice, and that's why we're not going to look at it too much afterwards. But I want you to understand the underlying complexity of so what's going on. Okay. Okay. So this, let me say that this region here is going to be the set of points in R2 such that phi of S of X equals S5, right? That's what this region is here. Okay, so in order to define that region, I really need to be able to find these green lines here, right? Just the same way before here in one dimension, if I could define these green bisectors between the nearest neighbors of the sites, then I can define these regions, and I can do binary search to find stuff. Okay, so in order to define these regions, the first step is actually to define these edges. Okay, and this will be called edge 1, 2. Okay, and if I write this out, it's going to be this set of points in RD such that the distance from X minus S1 is going to be equal to the distance from X minus S2. Okay, so it's where the distances are equal. This is the bisector line in between these. But this also needs to be less than or equal to the distance from X to Sj for all j not equal to 1, 2. Okay, so it also needs to be less than any other distance, right? So that's because if I were to extend this line here, well, now it's closer to S3. So that is not part of it. So I don't want to define the entire line, which is this bisector line, but I want to define kind of this region in between here, where this is well behaved, right? Where this actually defines part of the diagram. And so the difficulty is not just finding these bisector lines, but finding the ones when they actually exist. Okay. Another important part of this is going to be these vertices, and this will be vertex 2, 5, 6. Vertex 2, 5, 6. Okay. So this vertex will be defined by S2, S5, or S5 and S6. Okay. And this will be equal to the set of X in RD, such that now the distance has to be equal to 3 points. S2 equals to the distance between S2 and X is equal to the distance between S5 minus X is equal to the distance S6 minus X. Okay, and this has to be less than or equal to the distance between Sj minus X for J not equal to 2, 5, and 6. Okay, so this vertex is the set of points. It's actually only a single point where the distance is close. The closest distance is equal to S5, S6, and S2. Those are all the same distance, and that's closer than any other distance here. Okay, so there's actually this. Let's see. There's a circle I can draw, and let's see how well I do at drawing this circle. That will look like this. Okay, this circle will be centered here. The center of the circle is at this vertex, and the radius is equal to this distance to these 3 points. So they're all exactly on the circle, and no other points are in the circle. Otherwise, they would be closer. So S4, notably, is not inside the circle. And I don't know if you remember when I was initially laying out these points, I almost drew S6 a little bit different spot, and I spotted that there was almost going to be a tie, and that would kind of be confusing when I was explaining this to you, so I moved it. All right, always thinking about that. Okay, this is the structure that's going on. Okay, so you can define these things by it turns out. So let me tell you some good facts about this Voronoi diagram. In R equals in R2, okay, you can let's see, the first thing is the complexity. The complexity of the Voronoi diagram is going to be O of K. So what does this mean? This is the number of vertices and the number of edges. Okay, so if everything I need to describe the structure is linear in the size of the number of sites in R2. Okay, basically, I'm drawing a planar graph, right, through a bunch of vertices I need to find. Yeah, so I need to argue that. Yeah, so it's I'll explain why this is true. I'll talk about the dual structure in just a second briefly, and they'll be associated with the planar graph, and a planar graph is linear in the size. I don't have too many edges, right? Potentially, I could have k squared. You could have k squared of these edges. Every pair might cause a bisector, but most of them don't exist. Okay, so in R2, most of the bisectors and potential vertices don't exist. There are only O of K of them. So the size is linear, which is great. It means I don't need to store extra space just to store this function. So I can compute in O of K log K time. There are different models of computation under which thinking about computing this, but it's basically kind of K log K time to compute it. Basically equivalent to sorting. You kind of do these sweeps of the plane, and I'm not going to get into it. And once I have it, then I can solve for this function. I can do something like a binary search in O of log k time. Okay, so I can efficiently find the closest thing. I can do something like build like a binary tree. You kind of need to build it two-dimensionally in some way. I'm not going to get into it, but I can solve for finding the closest thing in logarithmic time, the same way I could in just one dimension. So that's great. Okay, so the bad news. The bad news is this is not true for d greater or equal to 3, right? When I get to 3 dimensions, stuff starts to break down. So the complexity in R3 and R4 actually is going to be O of k squared. Okay, so this means that at least a constant fraction of these bisector edges are going to exist. Okay, so I can't get away with saying, okay, they're only kind of a number of edges on average every cell. That means that in 2D, on average, every cell has a constant number of these, even as it gets really big. Most of the stuff are far away and don't cause these bisector edges. Okay, but what's worse is that the complexity in general RD is going to be O of k to the power d over 2, and it's this ceiling of this. Okay, so in general, the complexity grows exponentially with d. How does this make sense? There are only k squared bisector edges, but there are going to be more of these vertices. And actually in high dimensions, there are these kind of faces of, intermediate of mixed dimension here. And so just storing this function is going to get really complex and grows exponentially with the dimension of the space. So this is part of the curse of dimensionality. Okay, the curse of dimensionality is this thing where basically I like to think of it as when you draw pictures, as most pictures are in 2D, things look nice and simple. And when you get to high dimensions, things get really, really, really complicated. And they don't work at all like they do in 2 dimensions. And this is just one way to quantify it. So stuff becomes really complex trying to describe this totally precisely in high dimensions. This was really not the case for projection. For projection, it kind of was, I could do this with the dot product. It grew linearly with the dimension, the complexity of this. This grows really exponentially with the dimensionality here. So this becomes very tricky in high dimensions to analyze this sort of exactly. Oh, so how do you determine what the value of k should be? That is an excellent question, and I'm not going to completely answer that, but I'm going to give some insight into that in the next lecture, which will be on Monday. Yeah. So in this case, in this problem, these are for a given set of sites, which are just defining how do I assign points in the clustering. I haven't talked about an algorithm yet. These are not the data. I'm using k, which is the number of sites, not n, which is the number of data points. The number of data points are going to live in this diagram, and their mapping will be defined by this function. Okay. Let me say 2 more things, and then we'll start talking about the specific formulations, and I'll show a short demo in Python. Okay, so we're going to have this phi of s function for s equals s1 up to sk, okay, of x. And so in high D, this is going to have very high complexity just to define this function, okay? Let alone try and compute the function, okay? I said in 2D you can compute it in log n time. The good news is that if we remember what this function is an argmin sj in s and sj minus x. So I'm just trying to find this minimum point. I don't need to build a whole function to actually compute this, right? To totally understand what's going on and totally make sense of it, you would need to understand this in high dimensions, but we don't need to do that. Well, our algorithms will just have to compute this function. And so I'm going to have a simple function here. So 0, I'm going to set s equals to s1, and I'm going to have a I equals to 2. Okay, and then I'm going to have a for loop for so for I equals 2 to k. Right, so I don't need this guy here. Then I'm going to say, let's define this m, which is the distance between x and s1. Okay, and I'll say if m is greater than the distance between x and si, then I will set s equals to si. Let me move this over a little bit. S equals to si, and we'll do and m equals to x minus si, right? And then 2, just return s. Okay, so there's a simple function that you can solve this, and this function is, O of k time. Okay, so I can write the simple for loop to solve for the closest distance, and I don't need to actually build this Voronoi diagram in order to solve it. I can just compute it by running a for loop. Okay, and so this is how we'll use it, and this will be an abstract solution. So we're going to have a little bit lack of understanding, but we'll be able to use algorithms which can still compute this function. So that'll make stuff so we'll still be able to do stuff, but understanding it is going to be tricky because of this cursive dimensionality. Okay, I want to spend I want to just spend a couple minutes telling you a really kind of important thing where this Voronoi diagram comes up in things like things like computer graphics, where I draw this Voronoi diagram in between these sites. Okay, I want to show you another cool structure that's, and maybe this isn't perfect here. Okay, so assume this is the Voronoi diagram of these sites. There's something called the Delani triangulation, which is going to be I'm putting a bunch of basically triangles on these points. Okay, good. And yeah, okay, so this is a way of putting a triangulation. So if you're doing computer graphics, you actually build 3D models by a bunch of triangles that kind of fill in the space, or you build terrain models by you interpolate along these triangles where you actually have data at these vertices. And so these triangulations often come up in a lot of other applications. And this Delani triangulation is kind of the most stable, the best one in a lot of measures. Its minimum angle of anywhere in the triangulation is, for any way you can triangulate the point sets. There are lots of ways you can put down triangles that cover stuff. But this is the one where the minimum angle is as big as possible, for instance. And it's a dual of the Voronoi diagram, where every edge here corresponds with an edge. Every kind of vertex in the Delani triangulation corresponds with a face in the Voronoi diagram, and every, let's see, what's the other thing? Every vertex in the Voronoi diagram corresponds with a face in the Delani triangulation. Okay, so these are dual, so they're the same complexity, and this is often the way you argue about the complexity of the Voronoi diagram, is it's the same as this triangulation, and so this might complete some of these arguments. I just think it's a cool structure that I was going to point out. Notice that the edges, like this one here, don't necessarily cross the corresponding edge. That's not necessarily true. Okay, so I just want to point out this kind of this correspondence. Okay, great. So let's get back to the exact formulation now. Now that we had this kind of detour of Voronoi diagrams, we're going to have again our input. We're going to have X, a subset of RD. We're going to assume the distance is Euclidean, and we're going to be given K. Okay, so now assignment-based clustering is going to, the goal is going to be a set X of these sites up to SK, which are also going to be in RD. It's a subset of RD. Okay, and which with the goal of to minimize some cost function over the choice of S. Okay, I'm going to minimize, so I'm going to find the set of these sites, which is going to be my model, which is going to minimize some function of the set of xi minus phi of s xi. Okay, so I'm going to do some function, and the most common functions are for f equals just the sum, f equals the sum of these residuals. Let me write it out this way. So it could be the sum of the residuals, the sum of the residuals squared, or f equals the max of these residual values. Okay, and these are three different formulations. This one is called the K median. This one is called the K center, and we talk about both of these in the data mining class. Particularly the K center one, it has some really cool and nice properties and nice algorithms. This one is called K means. Okay, so this is the one that we will talk about most in this class, probably the most popular formulation of clustering. Sites are not given. You have to find the sites. The goal is to find these sites here. So the same way we found this regression function, we found the k-dimensional subspace and dimensional reduction, we need to find these k sites. So we need to figure out where to put these k sites. And so you can imagine with this Voronoi diagram defining this structure, this is a more complicated problem. And our solutions are actually going to be, there's going to be a very simple, very popular algorithm called Lloyd's algorithm, which we're going to talk about. It's the results we can say about it are not going to be nearly as satisfying as these other approaches. Okay. Okay. So just to write this k-means clustering again is to find this S1 up to SK to try to minimize over S this sum of the xi minus phi of s xi squared. Okay, so we're going to try and find this sites s that minimize this here. Okay, so we're going to go back to this here. This picture here, we're given these points x, and we need to find these, the centers here. We're given these black points x, we need to find these blue points, this model s, that are these 3 points that are at the center here. Yeah, so in the previous picture, yeah, great. Previous picture, we're defining, this diagram is for sites that are already existing. So we're going to have to try and optimize this diagram, which is actually a very complicated problem. And so, you know, there's research in computational geometry basically that studies how do we do this and how hard is this? And it turns out it's really messy problem to do this exactly. And that's not what anyone uses. So I'm not going to tell you about those algorithms. But this has been studied. It's just very complicated. And we're going to use a different algorithm, which will be a lot simpler than those, but its guarantees and what we can say formally about it is going to be much weaker. So, and that's kind of what I'm trying to motivate here. Okay. Okay, so this is going to be our goal, the K-means clustering problem. And we're going to be describing an algorithm. And the algorithm, I'm hoping I've set it up enough in this lecture so you think this sounds hard, and then you're going to see the algorithm, you're like, oh yeah, that sounds like a really, it's so simple, it's you know, and we'll see that. And a lot of time it works pretty well. Okay, so there's also, I'll mention, yeah, let me mention while I'm on this slide, there's another variant of this called K-medioid, okay, so, which is minimizing the sum of the residuals, but this requires that S is going to be a subset of X, okay? So in general, the sites could be anywhere, right? In the pictures I've shown, the sites are not the data points, but sometimes it makes sense to restrict that the sites have to be the data points. In fact, that's called the K, and then they usually use the sum of the distances instead of the sum of the squared distances. And we'll talk about, the next 2 lectures will be basically why do we use the sum of the squared residuals. But if you don't have those algorithmic advantages, or as we'll see, the statistical modeling advantages, then it actually makes sense to, if you're restricting them to be data points, then it makes sense to be just the sum of the residuals. That's less, outliers don't affect this cost function as much. Okay, so just to clarify a question, if phi of s is a function that determines which site x belongs to, yeah, so phi of x is a function determining what sites, yeah, what site a point belongs to. You could think about, so dimension, so reduction, okay, and we have, let's say, let's call it, so K means, well, PCA, K means clustering. Okay, so we're going to have these two different things. In this one, we're going to have K, so basis functions. These are going to describe the model. We're going to have V of B is going to be V1, V2 up to VK. And here we're going to have K sites. And each VI is going to be, this is going to be a unit vector, and VI, VJ are going to be orthogonal to each other. We're going to have K sites. So S equals S1, S2, up to SK. Okay? So this is going to be the same for both of these. Here we're going to have the assignment is going to be done by this projection function. So this is by projection. Here the assignment is going to be by this phi of s function, right? So this is kind of the nearest neighbor problem. These are both finding the minimum point. This is equal to the arg min point B on this basis B minus X, right? It's going to be very similar that this is arg min an element S that's minimizing X minus Sj. Okay, so there's a very similar kind of thing that's going on here, but we're but we're minimizing onto a point set instead of onto a subspace. So it's not going to be convex anymore. So when we talked about convexity, so then with gradient descent, we're not going to have convexity now. So this is going to make this harder to optimize. We technically didn't have convexity when we used the power method, and it was kind of like a gradient descent thing, but it worked out okay. We're going to have even weaker properties here. Okay, and then yeah, and so then the goal is going to be the sum of these residual squared, which is going to be the sum of xi minus projection onto B of xi squared, and this is going to be similar here. The residual squared, which is the sum equals 1 to n of xi minus phi of s xi. Okay, and squared. And so again, the goal is going to be to find, right? I have to find these guys, right? So I want to, these are either what I want to find in these algorithms. And it seemed like, how can we possibly do this for dimensional reduction? But the SVD and all this structure it had kind of gave us the solution. With Kmeans, we're going to have to come up with an algorithm kind of from scratch for this problem. We can't automatically use linear algebra. Okay, I want to tell you one important fact that we saw earlier, but I'm going to say it extends to higher dimensions. If we have a set X, which is going to be equal to x1 up to xn, and I want to find a point S to minimize the sum of I equals 1 to n of just s minus xi squared. Okay? This is actually something we've looked at before. We've looked at this, so for xi in RD. We've looked at this in R1 before. In R1, we already know the solution for this. We looked at this when we were doing the Bayesian inference thing. We assumed that there was Gaussian noise model, and we want to find the map estimate, the maximum, or the maximum likelihood estimate, which is the point that maximized the likelihood of these things, and that turned into minimizing the sum of the squared distances. Now we're doing this in vector space. And if we remember what the squared distances are, if we remember that xi minus s squared is going to be equal to j equals 1 to d of xi j minus sj squared, right? The distance is the sum of the squared basis vectors, right? So, right, if we have the axis, this was xi1, xi2, right? And I want to measure the distance in between 2 points. This is xi, this is s. The squared distance between them, this is xi minus s squared, that's going to be equal to the sum of the squared distances on the axes. A B, I have xi minus s squared is equal to a squared plus b squared. And this is true in higher dimensions too, right? So I'm getting the sum of the Euclidean distance is the sum of the individual things. So if I want to, of the individual kind of the dimensions, so if I want to find the thing that minimizes them, I can do this one dimension at a time, right? So that means that the solution here, the solution is going to be equal to S equals 1 over n. The sum equals I equals 1 to n of xi, right? So the jth coordinate is, I'm doing this element-wise. Remember, when I add or divide vectors, it's element-wise. That's xij. So this coordinate-wise solution, this one we've seen before. This is one-dimensional problem. But it turns out the solution in high dimensions for sum of squared errors, I can do element-wise, and I get the right solution overall. So if I have a set of points, this is my set X, the point that minimizes them is the average in this direction and the average in this direction, and I can create those two coordinates, and that gives me the point that minimizes this error. Okay, so we already know how to do this for one center. For one, when k is equal to 1, this is basically our solution. Okay, but when k is bigger than 1, this becomes, that's when it's interesting and for clustering, and now the problem is kind of a lot messier, which is more convex. Okay, I want to quickly switch to a quick demo in Python. See if I can bring this up. Okay, great. So this is, I linked this off of here, this collab file. Okay, and just so I can see the chat. Okay, and so what do we have here? I've done this in NumPy pyplot, and there's this library called sklearn, which has a lot of functions built into them. I don't want to put this up front because if I just point you to them without explaining how they work, you're going to use them probably in the wrong way. So that's what they do other places, but not how we teach it here. But it has some great built-in functions, and I'm just going to show you how one of these work here. Is one thing it can do, it can just make blobs, which is going to build this data set for me. This is 100 data points that have clusters. Okay, so in order to run clustering, it won't make sense unless we have points that have clusters in them, and it has something that makes clusters so clustering works. Again, pointing out that this should not be assumed that there are clusters. Okay, and I said there are going to be 4 of them here. So let's, I get these 4 clusters in space. And then it also has this Kmeans function, which we'll describe next time basically how that runs. I'm going to, and it's going to give this thing, which is going to have a fit function, which is basically this phi function, which is telling you how to, and this predict is going to give me the label 1 or 0 through 3, or basically 1 through 4. And so it's going to, yeah, so this is where it, yeah. Okay, so I'm going to run this, and then I can basically plot the output. I'm going to plot, I get these 4 different centers it found. Okay, and then it colors them based on their label. These are all assigned to this cluster. The purple ones, the green ones are assigned to this cluster. The blue ones assigned to this cluster, and the yellow ones assigned to this cluster. Okay, so this is what the output of clustering should actually look like. And here's the built-in algorithm, how to do it. We're going to explain what that algorithm is, and for the most part, there are some nuances I'm going to go over because of this Voronoi diagram that come up, that it doesn't always work, and you have to build in these other cases. Because that, I don't think I'm going to ask you guys to write it, because it can be a bit of a mess to handle all the corner cases. Okay, but in practice, this is what the output is going to be. Okay, and next time we're going to see why we're going to describe Lloyd's algorithm, which is going to be the core algorithm for solving K-means clustering. And we're going to kind of give a sense of why it works, how to think about choosing the number K, which I've said so far is going to be inputs. And we're going to look at some of the limitations of this algorithm. Okay, great. So we'll stop there. And don't forget the quiz is going to be on Monday. That'll be about dimensionality reduction.